So we have understood what is PMOS and what is NMOS, right? How to turn on the PMOS and NMOS transistor. It's time for us to understand something called as complementary CMOS logic. Complementary CMOS logic. To design the basic combinational and sequential circuits, what you have studied in the digital electronics. First, let us design a simple NOT gate, which is nothing but an inverter, a logic gate. Okay. First, let us design all the logic gates using this complementary CMOS logic. Complementary CMOS logic, it has some advantages and disadvantages. We will discuss that later. First, let us design a circuit. You will be able to understand it, right? So, NOT gate, inverters, right? When you come to the logic design, so first of all, let us come step by step. When you directly come to the logic design, the logic is very simple. This is the symbol of a NOT gate. If you apply 0, you should get 0 or not. If you apply 0, you should get 1. If you apply 1, you should get 0, right? That means whatever be the logic you are applying, you should get the complement of it. That is what we mean by a NOT gate or an inverter. You have to invert the bit. If you apply 0, you should get 1. If you apply 1, you should get 0. That's it. So the truth table is very simple. You have only one input and you got one output. If you apply 0, you will get 1. If you apply 1, you will get 0. So very simple truth table. So this is nothing but the logic design. So we have designed the logic, right? Now we are going to implement this in using PMOS and NMOS, what we have studied already. So in the previous video we understood PMOS and NMOS, right? So we are going to implement this using that. Okay, using that we are going to implement, right? So in actually designing inverters is very simple. From the next video onwards we will be designing some complex gates. For that I'll show you some design procedure. Now the idea is very simple, like y equal to x bar, that is the y equal to inverted version of x. That's it, right? This can be formed when you are having one NMOS and one PMOS, and if they are connected together, if they are cross coupled together like this becomes the input x, and here you have to take the output, that is the intersection point of the pull up network and the pull down network is called as y, and this whole network is called as pull up network, which will contain only PMOS transistor. This whole network is called as pull down network. And anyway, this is a simple circuit, so you have only one transistor, but in many circuits you will be having a lot of transistors, right? So PDN, this will contain only NMOS transistors, right? So this is the basic inverter circuit, which is nothing but a combination of both PMOS and NMOS. Now let us verify this circuit. Basically, how to verify this? Very simple. If you apply 0, you should get 1, right? If you apply 1, you should get 0, right? So this is the input, right? If let us say I'm applying 0. If I apply 0, can you guess which transistor will be on? Can you guess which transistor will be on? I already told you that if you apply 0, PMOS will be on and the NMOS will be off, because that is how it works, right? This we have already seen. So PMOS will be on, NMOS will be off. Okay, since PMOS is on, it will be working, NMOS will not be working, so forget about NMOS. PMOS will be working, and you see that PMOS is pulled up to VDD. PMOS is pulled up to VDD. So this node, the output node, will also be pulled up to VDD through PMOS. Understand that in VLSI design, whenever the transistor is on means we consider a short circuit. Which will be typically drawn like this. That's it. This is VDD and this is out. Okay, and here no connection because the transistor is off, and if I give 1, this is 0, this is the situation, right? So whenever the transistor is on means there is no transistor, it is shorted, a single wire. So output is pulled up to VDD, which means that output is logic 1. Output is pulled up to VDD. Output is pulled up to VDD. VDD means logic 1, right? So you are getting logic 1. If you are applying 0, you are getting logic 1, because the PMOS turns on and the PMOS makes a short circuit through which the output can be pulled up. The output can be pulled up. Now let me explain the other case also, applying 1 also, right? If at all, if I draw the same circuit, this is the CMOS inverter. If you apply, this is the input. If I apply 1 here, PMOS will be off and NMOS will be on. This is the output. So from this it's very clear that I'll apply 1, PMOS will be off and NMOS will be on. PMOS is off means this is inactive, and NMOS is on means this forms a short circuit. So there is a direct connection between the output and the ground. So the output is actually pulled down. That means the output is actually made to ground, which is again the output is made 0, logic 0, because the output is pulled down to ground. Ground means logic 0. So the output is logic 0. If you apply 1, the output is logic 0. So the conclusion here is, if I apply 0, PMOS will be active, so that it is making the output logic 1. If I apply 0, PMOS will be active, making the output as logic 1, because it is pulling up the output node to VDD. When I apply 1, NMOS will be active, so it is making a short circuit and is making the output to be logic 0, because it is grounding the output, it is pulling down the output, so the output is made 0 in this case. So this is basically an inverter which is using both PMOS and NMOS. Since we are using PMOS, both PMOS and NMOS, this is actually known as a CMOS inverter. Okay, very basic circuit, very important circuit too, a CMOS inverter, right? Thanks a lot.